Hey everybody, I'm Erin. It's nice to meet you. We're here to talk about the mechanics of metrics. Um, a little bit about me, I am now a creator of things at Red Hat. I spent 21 years creating things at IBM, also leading things and architecting things and a bunch of other stuff, but it's kind of nice to get back to development as most of my job at the moment. I'm also a dungeon master for 11-year-olds and I love building ridiculous things. My most recent ridiculous thing is an application amazingly named Monster Combat. It takes Dungeons and Dragons monsters statistics, stat blocks at least, and pits them against each other in a fight to the death to give me application metrics to work with. This project started for Spring One in 2019. I gave a talk on application metrics. I used this as a source. I had intended, I spoke about application metrics at DevNexus last year using this talk. It was the last like in-person conference before everything happened. And what I had intended for that conference was to have Spring with micrometers sitting side by side with Quarkus and microprofile metrics. And sadly, microprofile metrics has some significant limitations that make that very difficult. The result as that talk concluded, what I did next was I had gotten Micrometer working with Quarkus for the talk, and I turned that capability into a proper Quarkus extension. And that extension was then merged into part of Quarkus Core on my first day at Red Hat in September of 2020. So that was pretty fun. So as of Quarkus 1.9, the micrometer extension is the preferred way for you to gather and instrument your application with metrics, or to instrument your application when you're using Quarkus. And I hope by the end of this talk you will understand what the shortcoming was and why I had to do that. When we're talking about metrics, we'll come back to all of that, right? We'll come full circle. But when we're talking about metrics, we are talking about time series data. Time series data is just a series of measurements. When you end up plotting it, time is usually the x-axis. Your data values end up being on the y-axis. Ideally, this data is gathered at regular intervals. Of course, since it's a distributed system, you might have sometimes when it's, when a scrape is dropped, or when it's delayed because of whatever's going on in the network at the time. Most monitoring systems do have, they all have ways of trying to get around when that happened because it's more or less inevitable. But we're looking at a string key and associated with a value. Now, the other part that we have are tags. And so here's an example using the simplest data type there is, a counter. This is using the micrometer library where we take the registry, we specify the counter that we want to increment, and we specify that with a combination of things, both the string as the name. Note this is a micrometer convention, it has a dot because micrometer is going to then do some Prometheus specific naming conventions, right, to get the name the way Prometheus wants it. But for the purposes of consistency across the code base, we use a dot in the name. And then we specify some additional labels, the die, which die we're rolling, and the face, what was rolled. And then we increment that counter. That combination of that whole combination, right? That's what we call dimensional data. We have that one measurement, but we have these other characteristics, these labels that help identify, they provide additional information about what that measurement is. When we talk about cardinality, each combination, each unique permutation of the string value plus those tags and their values becomes a new data series or a new time series, right? And we then can use those tags to re-aggregate, splice, dice, group, right, chart. We can pull meaning out of this vast pool of data by evaluating it or grouping it using those labels and tags. because we have so many possible permutations, in this case, thankfully, we're bounded. We know how many types of die there are. We know how many, like the max number of faces is a d20. We don't have to go very much higher than that, right? Um, because we have that, we're not going to get out of control. We got, a little over 10,000 choices max. You can easily see, because of the way these permutations compound, when they talk about a cardinality explosion, that's what they mean, right? Is that if you're not careful about the possible values you're using for these tags, you can get a lot of data very fast, and it's just way more than you intended, and you can totally flood your system. So care must be taken, but don't be discouraged. And I hope to try to show you that when you have some robust data, you can really learn some cool things about what's going on in your app. So don't be afraid of it. Just be cautious. It's a balance. Let's play just with those counters so we can look at how those behave. Basic counters, if I look at dice rolls total, so you can see what it looks like in Prometheus land, it's showing me, oops, I added a graph. That's not what I meant to do. I meant to do that, right? So it's showing me, here's d10, what face was rolled. I've got the instance and the job, which were collected or which were added. Those are additional tags added by the Prometheus scrape itself. And then I can see the counts. You can see some of these, like I haven't restarted that Quarkus Micrometer native job in a while. It's got some really high numbers where the other ones are lower. Okay, so that's fine. That will become relevant in a moment. Let's look at a new dashboard. So if we try to plot this count, dice rolls total, we're like, we can just look at that and we'll do let's just do the last hour. Let's save this, save. I want to make sure we're refreshing, but like not too frequently. Let's do that. That's like blah. That's just a blob. That tells us nothing. And it's because we're trying to plot all of those unique data series at the same time. It doesn't work. Like, that's not telling us anything useful. We want to aggregate those in a useful way. So let's aggregate them sum by die. Let's look at it that way. And we say, oh, hey, all right, so we've got 10, 12. We can see the D20 is way up top, right? And a D4 is way at the bottom. Okay, so we can get some idea of how they are related to each other in a relative sense. That's fine. We can even make the label prettier. That's great. But it's like, it's telling us, it's giving us a little warning here. And I wonder why it's doing that. Now, if I show 3 hours, this is why. So I told you, remember, these two processes, they have a much smaller value. Their counters have been reset because I restarted them. And so here's what happens if you plot a raw aggregation of counters on a graph and those counters reset. You get a big jump, a big chunk off your data because you just rolled over the value to 0. Now, when you're working with, you can see very slowly, just by volume, right? This value is kind of slowly creeping up again. It's such a big value base that it's hard to tell. You are on an increasing slope there. We also know that even if we weren't restarting process, let's say we were back in the olden days where processes lived forever and we went way out of our way to make sure they never start, your increasing values, you're going to reach max int at some point, or max whatever it is, and then your counter is going to roll over and you're going to get this anyway. So Grafana is being very helpful here. It says you're using Prometheus and this is a counter. You should apply the rate function. So let's do that. What rate does is we specify an interval, let's say 1 minute, and that's going to establish a sliding time window. And what Prometheus does over that time window is it takes all of the values in that window, and the data point then is the average of those. So you've got that sliding time window that's taking, so like at any one point, it's got the minute that's before it. It's taking all of that data, and that average is then that data point. Now, that totally changes the shape of this graph. We no longer have this ever increasing value because we're now looking at the rate of change of that value per second as calculated over this sliding time window. And that allows the other capability that the rate function has, in addition to converting this into a by second measurement, is it addresses that counter rollover. So if it, because it knows these are counters, they only ever increment, only ever increment. So if I measured a 10 and then the next point, data point after that is a 2, I know the counter flipped over and that should actually be a 12, right? And so it does that kind of compensation and then off you go, which gives you a nice pretty graph. So if I take this back down to like 1 hour, we can see, right, we have nice relative lines for our frequency. Basically, this is like frequency of use, and it's still a rate. It's like dye. This is the usage of the dye. We can, if we wanted to view this in a different way, like maybe we said this isn't the easiest way to digest the information that we're looking for, we could flip this into a series. And then you can see very easily, still based on the same data, it's just bucketed, right? I see. Okay, so a D20 is really used almost all the time, and a D4 is like a fraction of the time, which is totally normal. So that's what we can do. That's fine. That's great. Yay, we learned about counters. We learned about rates. Let's see what's next. Okay, hits and misses. I'm using hits and misses here so we can look at a different kind of data being collected. What you need to know in Dungeons and Dragons is that there's different ways of hitting an opponent and causing damage. The first one is a comparison against an armor class. The attacker rolls the d20, and either it hits because they rolled a 20, which always hits, or they beat an armor class specified by the defender, or they rolled a 1 and they missed, or they were less than that check and they miss. There's another kind of attack which is against a difficulty. It's a difficulty class check, say. And in that case, the attacker just attacks and the defender is the one that rolls. When they succeed, they have the damage. So we've got a bit of a math difference between an AC attack and a DC attack. A critical hit in an AC attack does double damage. A saved throw in a DC attack does half damage. So we'll see how that plays out, but those are the main elements that you need to know. We're going to look at these using a distribution summary. When you're within micrometer, it says for spring or Quarkus, right? Doesn't matter. When you're looking at micrometer, you're going to register a distribution summary. And here again, we're specifying that string. It's round attacks. In my naming convention, it's attacks per round. And we're going to keep track of whether or not it hit or missed, what kind of attack it was, what damage type it was, and then we're going to record the value that we're recording is the damage amount. And it's only ever positive. If it's a miss, it's 0, and otherwise we get more damage. By default, out of the gate, out of the box, micrometer will then record a count, a sum, and a max. This also applies for timers. So micrometer timers are exactly the same as this. The only interesting bit about timers is that they know they're dealing with time. So they will do whatever conversion is necessary to make sure everything is consistently dealt with in terms of time units. So that's your only difference really between timers and distribution summaries. But you get your count and your sum and your max. I can, if necessary, use additional configuration to turn on histogram buckets or to turn on pre-computed quantiles. But I am not a fan of that plan, and I hope you'll understand why. Let's see what we can do though, just with the count and the sum to begin with, right? So if we look at the count and the sum, what can you do with a count and a sum? You can calculate an average. So we already know that we're going to use a sum because otherwise we just get a mess. And we know we're going to use a rate. And we know it's round attacks sum. Like if we look here, we can see round. Here's your round attacks sum. We can look at what this data looks like. If we execute this query, here's round attack sum. We can see it has the attack type, it has the damage type, it has hit or miss, and it has the instance in the job as appended by Prometheus. You can see sometimes there's zeros. This combination of tags has not occurred recently. Remember, we've restarted some things, so it may have happened in a previous run, but right now that value is 0. You can otherwise see some pretty big values here. So let's look here. However, we need this rate over 1 minute, right? So we've got our rate over 1 minute. That's like an overall sum of damage. That's like damage per second. You don't really know anything else. It's just all damage per second. So let's make that a damage per attack, which means we need to do this sum, and we'll do this over a count. This is damage per attack per second. Okay, so that's average damage per attack over a second. That's interesting. But we know we have more data than that. This would be overall, we can say. For example, what happens if we take this query and apply a dimension? Let's do by hit. Ooh, I like to do my syntax miss, hit or miss. And we need to apply that also to this series, right? So we've got hit or miss. We're going to hide the overview, the overall now. If I do this, we can see, okay, so we've got we know there's some types like misses and critical misses. Those don't have any damage. They don't show up in the graph. That's fine. But we can see from here, critical hits consistently high. That's normal. They're double damage, right? The hit, well, that looks okay, average. But this red line is kind of like, sometimes it's higher, but that's a saved hit. But you know a saved hit is actually double. It's a half, right? So you know the hit that would have been associated with this was way high. So where did that data go, right? Okay, wait, hang on. We're missing something. Let's do, let's throw attack type in here. Let's see what we have. We have both attack type and hit or miss. Put the tag in a better place. Let's see what that looks like. Okay, so we've got AC, 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 and we've got two. We've got hits and saved hits and hits for DC. And you start to see that these are very different. Of course, the colors changed a little bit, so it might not pop out at you. Critical hits are about the same as they were before we split this out. Critical hits are about the same. The misses don't apply. The attack, see, I can't do that. It takes the scale off. The attack, in an armor class style attack, you can see the average is still holding really steady. It's got a nice clean average. This is the most common type of attack, the most common thing. So, okay, this makes sense right there. But here's where things are interesting. Now this dark blue is the saved AC. You can see it's dancing around, right? It's still dancing around. This big spiky red line, those are the DC hits. It's when you didn't save it, you got full damage, and you can see some of these are ridiculously high. And this was just an experiment. When I was first learning about this, I hadn't realized that they were like quite that bad. Now, what's interesting is the spikiness of this data. And if you look at this in a different way, we can say, let's do the sum of just the count rate of round attacks count over a minute by, oops, I keep wanting to do that other syntax, damage by attack, hit or miss. And we're looking at all right, so here's our floating average. You can see like this might be a little hard to see because some of these things are way down at the bottom, but you realize that they are really low. So let's just flip this over so we can see it, and we'll take that to the series. Okay, so when we put these things next to each other, right, you can start to see that there's a little bit more going on here than you might expect, right? So we have critical hits, critical misses. The critical miss isn't going to show up here because it doesn't do any damage, right? But these are equally common, right? That average is there's a bit of smoothing and extrapolation going on here because that's not very frequent. The AC style hit, this nice solid blue line, it's nice and consistent, and there's tons of them. This miss isn't going to contribute any damage, so it doesn't show up on the graph. That's fine. These two are very, very sparse. You have within a second over 2,000 instances of an AC hit where you only have 73 of a DC style save. So your numbers for those two series are really small. It's going to be really choppy because Prometheus, that rate function, is extrapolating over missing data. There's going to be places where there's just no data within the interval, or within certain scrapes because it didn't occur. So it's doing some extrapolation and some smoothing, and that's why you get some really, really choppy data. Also, save values really are all over the place. You have some that are just tiny. They're tiny values. It's a little tiny poison save. And then you have some that are like, okay, avalanches. The last thing I want to note is that you can't correlate this high peak to a single incident in your logs because this is still a rate. So it's still got a minute's worth of data averaged in here. Somewhere in there, a really nasty attack happened, but it doesn't correlate to a single instance. What I have been doing here, and this is general advice applying for all observability scenarios, is I'm delaying aggregation to the last possible minute. I am regrouping the data that I have using dimensions so that I can, so I can get meaning from it. So when you hear about like read time computation, read time aggregation, that's what I'm doing. I'm waiting until the last possible moment to perform those aggregations, which means I have to have measurements that allow me to do that. If I go and look at what microprofile metrics will, and I'm going to use a different metric because it has fewer tags so we can see it clearer. I'm just going to look at attack success. And this is as collected by microprofile metrics. I still have an attack type for this measurement. I still have whether or not it hit or missed, but that's really all I have. The value that I'm measuring in this case happens to be a difficulty class. So I could try to make an estimate about why something hits or misses and how those values compare. Now, if you look at this, I'm basically still creating separate time series for each client calculated quantile. So I've got a higher degree of cardinality because each quantile counts as a separate tag. It would be the same with buckets. So if you have 10 buckets, that increases the cardinality that you have in your data. So just bear that in mind. Now, the problem with pre-computing these quantiles is that they are unique to the process that computed them. And by the time they get here, I no longer have the set of data that created those quantiles. So here we're looking at an AC style attack. These are critical hits across one instance of Quarkus that's in native mode, one that's running in JVM mode. The range of the first one is 16 to 22. I'm just looking at the range of the values, right? The other one is 17 to 22. Why is one 16 and one 17? I have no idea what the data is that put it in that quantile bucket. I have no idea. If we look and try to find some others that are different, here's 16 to 22, but you can see the curve shape. If I was going to plot these hits, the curve shape would be different. So in the native thing, we go from 16 to 18, and then across 22, it's pretty flat. Here in the JVM mode, we have 17, 18, 20, 21, 21, 22. So it's not very flat. It's kind of an increasing, like if you were going to draw that histogram shape, it's not flat. And so I can't safely put these values together. They cannot be recombined. So if you're going to use client-side computation for quantiles, understand that's a dead end. You can plot it once, you can have it show up on a graph. If you need that precision, by all means, get there, but understand that you cannot combine that with quantiles calculated in any other process because you've lost all of the data that led to that measurement. When you're looking at histogram buckets, if you stick with bucketing, you're okay. You can still because you're just still dealing with counts. So as long as your bucket boundaries line up, you can still reaggregate across those buckets based on tags. So if you want to get histogram data, make sure you're using buckets and not quantiles, unless and until you absolutely need that client instance, that single service instance to calculate that quantile data. And so this is why I created the micrometer extension for Quarkus, is because this is not sufficient. This is not data I can use. It's not data Prometheus can safely use. I can't do anything with this data. It's a dead end, effectively. Okay, let's get back to this last topic. We'll see if we can get through the last 5 minutes. So what we've just looked at for metrics is one part of a larger topic called observability. Depending on who you talk to, they get a little annoyed if you try to talk about the pillars of observability, and I have to say I actually kind of agree with that. From a generic definition sense, you know what observability is. You want to be able to understand what's going on inside a system based on what comes out. I have a manufacturing background, believe that or not. My dad is a mechanical engineer, and I spent a summer as a college person in the quality control office at a manufacturing plant measuring parts. Why do you do that? Well, you sampled parts and you do all your measurements on the parts, and what you're looking for is a change in the trend so that you know that the tool needs to be changed on the machinery. You're looking at the output, you're looking at the result of the manufacturing process, and you're trying to make sure you can then make some determination of like what part of something else is going on in the process that has to be addressed. Fine. Who do we have participating in our distributed systems right now? Let's look at Kubernetes, or before that, Cloud Foundry, where you have an automation trying to orchestrate all of the bits and pieces that are running around your system. They want to be able to observe your services and understand how to interact with them. Yes, this is what health checks are for. And of course, when we're talking about Kubernetes, it's less about a single health endpoint and more, it's a little more fine-grained than that. You have a liveness check. Am I a zombie? Should you kill me? That's your question. And then there's a readiness. Can I handle work, or should you leave me alone for a while so I can recover? Those help Kubernetes observe any given service to understand how it should deal with it. Additionally, now from a metrics perspective, Kubernetes is able, you can configure Kubernetes to look at a measurement or a set of measurements and say, if these thresholds are exceeded, we need to create another service to help address the situation. And then once this falls below this threshold again, you can take those instances away, and it can start looking at configured metrics to make those decisions. From a developer perspective, just me, right? I find metrics useful as a consumer. I found more bugs in my code because I couldn't do I couldn't test all permutations of monsters fighting each other. It just was not feasible for me to do that. But it's easy for me to just set the requests up and let them go and then look at the trends that come out. I found all kinds of crazy stuff that I would never have caught otherwise. I found that really useful. We also know we can use these metrics for automated alerts. If something exceeds a threshold, if something shows a certain pattern, you can get a page. Great. That's all automation. That's awesome. There's a whole different section of work, right? That still falls under this observability umbrella, that's dealing with problem determination, right? What is actually happening? And really, to do PD well, you can't do that with the metrics on your Prometheus dashboard. And the questions that I see with people who are new to Micrometer or who are trying to understand what metrics can be collected, what I see is that there's a tendency to say, well, I want the exact URL that was used in my failed request. That's not what metrics showing up on a dashboard are for. That's where you still need your logs, and that's where you still need your trace. When we talk about trace, we're talking about distributed trace. And as you see Open Census and Open Tracing merging into Open Telemetry, and they talk about all of the kinds of data that you can gather for end-to-end tracing, that is where your diagnostics come from. That's where your problem determination comes from. And that has to be high cardinality data, you're going to offload it, right? You're not going to do, you're going to do as little computation as possible in the process. You're going to collect information and send it elsewhere. And then when you have a problem, you're going to be querying that data and working with that data without tanking your system because you're working somewhere else so that you can figure out what's going on. I think I'm about out of time, but watching what happens in the next couple months as we resolve metrics with the OpenTelemetry specification, I think the relationship between the two will be a lot clearer. But ultimately, you need to know application metrics are super cool. Just don't try to use them to debug problems. They just don't work. All right, thanks.